Welcome everyone to lunch. It looks like the most crowded lunch of the year, and for a good reason. We have some exciting science that will be discussed. We just heard an excellent talk by Bekki Dawson that used to be a graduate student in our department. We still remember that, but you're doing so much and you're blossoming scientifically and you're very proud of your accomplishments. I hope there is enough room for everyone. Today we are going to hear 4 presentations as usual, but they are split between 2 fields. When I was a postdoc, the most exciting, the most frontier field used to be cosmology, and we actually have 3 out of the 4 talks on cosmology, but there is a contender now for occupying most of the attention, and that's exoplanets. And we have only Bekki to defend that field, but you gave a colloquium, so I think it balances. We'll have 3 cosmology talks and 1 exoplanet talk. And the other thing I wanted to mention is that Alak Ray, that was with us for a sabbatical, I'm not sure if he's around, will be leaving tomorrow, and we hope to see him again for visits. So the first speaker will be Xingang Chen, and he is a professor at the University of Texas at Dallas, visiting us on sabbatical this year. We hope that he will stay for a bit longer, or much longer. And he will speak about primordial standard clocks, a direct measurement of the expansion of the universe early on. Then we'll hear from Bekki Dawson. She's currently a postdoc at Berkeley, a Miller Fellow, and she already accepted a faculty position at Penn State University. And she will talk about connections between super-Earth compositions and orbital architectures. And then we'll hear from Clem Pryke from the University of Minnesota. Where is he? Oh, over there. He will speak about something exciting. I'm not sure exactly the details, but the results were just arrived this morning. Was it?
Very soon.
Very
Within a half an hour.
The official title that was handed to us before he got his results was Improved Constraints on Cosmology and Foregrounds when adding 95 gigahertz data from the Keck array.
Wow.
And finally we'll hear from Professor Joe Dunkley from University of Oxford, considering moving to Princeton. Undecided. And she will tell us about the impact of tau on cosmological measurements. We'll start with Xingang.
Okay, thank you very much, Eddie. The 6-parameter standard model of cosmology is a great achievement of modern astrophysics and cosmology. Now we are working towards finding beyond standard model signatures. There are many different possibilities. In terms of early universe cosmology, the deeper question we're trying to understand by going beyond standard model are the following, at least 2 major problems. One is we try to understand what's the origin of a Big Bang, and second is what is the origin of the primordial fluctuations that eventually seeded all the large-scale structures in our entire universe. So we all know inflation is the leading scenario for the answers of these questions, in which it was proposed that our universe was once at the top of some potential, very flat, so it's a force vacuum, slowly rolling down. So the vacuum energy of this force vacuum driving the exponentially fast expansion of a scale factor of our universe. In the meanwhile, infraton field or some other fields do have some small quantum fluctuations. So those small quantum fluctuations was stretched into enormous superhorizon scales, which eventually seeded our large-scale structures. So the property of these fluctuations are superhorizon scale invariant, approximately Gaussian, and adiabatic for simplest models. So all this has been verified by a variety of experiments in cosmic microwave background and large-scale structures. So now the real question is this prediction uniquely from inflation? So indeed, in the past few decades, people have been trying alternative scenarios. They have a very different background evolution, like matter contraction, which is a fast contracting models, ekpyrosis, slowly contracting models. Of course, they have to be matched to Big Bang through a crunch and a bounce. And some of them, at least in some kind of toy model, do seem to reproduce or post-predict those observations. But I think it's fair to say none of them is as successful as the inflation so far. But I think it's fair we can take the following point of view for the sake of this talk. As far as model building is concerned, arguably, inflation has been the winner so far. But in terms of theoretical model building, the alternative scenarios and models, they will evolve with time, and people can improve it. So a more important question is, the more important question is in the experiment. So can we find a model-independent observational signatures that can be used to distinguish inflation from all those alternative scenarios? I emphasize model-independent because there are many possible beyond standard model signatures that we may discover in the future, including running of a spectral index, non-Gauss entities, tensor mode, etc. They all provide invaluable information in terms of model selections. But unfortunately, only very few of them can be used to model independently distinguish inflation from alternative scenarios. So by which, to illustrate model independent, let me just make an analogy. Let's say inflation scenario has several models, and alternative computing scenarios have several models. So most of the signals beyond standard model, if discovered, will of course select models in inflation scenarios. It can also distinguish some models in inflation scenario with some other models in alternative scenarios, but not model independently. So what we would like is some kind of this kind of signals, which its ability to select models in inflation is actually not the most important one, but it can kill model independently and alternative scenarios. So looks like we really need to go back to the definition of the inflation, which is A as a function of t is exponential. Can we directly measure A as a function of t of the primordial universe? We did that for our late-time universe. This is why we are convinced that we live in an accelerated expanding phase now. But can we do this for primordial universe? Tensor mode, which is well-known primordial gravitational wave, has come very close to achieving this goal. So for the sake of argument, let me divide all the scenarios into 4 types. One is fast expanding inflation, fast contracting, slow expanding, slow contracting. Some of them has names. Now, the tensor mode measures the amplitude of primordial gravitational wave, quantum mechanically fluctuating in the background, which is determined by the expanding speed of the background or contracting speed of the background, because those time-dependent background will create an effective thermal bath in which the primordial gravitational wave just pop up. So the tensor mode, because of the mechanism I explained, can be large in the fast evolving scenarios, but it cannot be large in slowly evolving scenarios. So if in the future tensor mode is large enough to be observed in any experiment, primordial tensor mode, it will rule out all the slowly evolving scenarios model independently, but the fast contracting model is still possible, phenologically possible. I think by now it's very clear why I say it's almost achieving the goal, because although tensor mode measures the magnitude of Hubble parameter, it doesn't tell the sign of H. So I'll ask this question again. Can we really directly measure A as a function of t of primordial universe? It turns out theoretically there's a proposal of standard clocks which says it's possible. So we can use the standard clock, the massive fields, which I will explain, as a standard clock to directly measure A of the primordial universe as a function of time. By massive field, I mean fields with mass larger than the scale of a horizon in a primordial epoch. So massive fields, on one hand, always exist. Even when we talk about single field models, we are talking about low energy effective field theories. So in the realistic model, they always have towers of higher energy states. So those are massive fields we need. And the massive fields oscillate in a standard way if their mass is large enough. It's just a harmonic oscillator. The ticks of this harmonic oscillator just behaves like almost like the clock, pendulum clock. So the oscillations will provide the ticks for time coordinate t, and those ticks will induce patterns of ticks in density perturbations, which I will illustrate later, which we will call the clock signal. So there are two types of primordial standard clocks determined by the way the oscillation is generated. The first is called what we call the classical primordial standard clocks, in which the oscillation of massive field is generated by just a kick, classical kick. In model building, it's sometimes called sharp features. So for example, this is the top of the flat potential of the inflation models. Otherwise, it will be scale invariant and very flat. But we know in inflation models, the flat potential is very difficult to find. So many directions in the beginning of inflation is very steep. So field just rolling down steep potentials and eventually find one slow roll potential. So those oscillations is a perfect candidate for standard clock. And even more generally, because a time-dependent background generates some effective heat bath. So as long as you have some quantum massive fields, it will fluctuate quantum mechanically, oscillates for a while, and go away. So this we call the quantum primordial standard clocks. So, okay, so next is how do these ticks of these clocks look like in terms of density perturbations? Let's look at a classical case first. So without the sharp feature, this would generate scale invariant spectrum. But the presence of the sharp feature and oscillations break the scale invariance. So the ticks, namely the clock signal, will manifest as some scale-dependent oscillatory features in both power spectrum and higher correlation functions, which we call non-Gauss entities. So this is the result to illustrate what the ticks look like. There's a lot of information there. Let me, for the sake of time, just concentrate on the blue lines. So the dashed line, which is a straight line, is the scale invariant power spectrum, and the y-axis is the fractional correction to the power spectrum, scale invariant power spectrum due to the clock signal. The x-axis is the scale. So as we can see, the four different scenarios, the clock signal are very different. In particular, as we mentioned, compared to tensor mode, the clock signal does tell the sign of a dot. Because if you look at the inflation model, the spacing between ticks increases as k increases, while for contracting models, the ticks decreases as k increases. For the slowly evolving scenarios, there's much fewer ticks than the fast evolving scenarios. What about quantum primordial standard clock? So as I said, one advantage of quantum primordial standard clock is it does not require sharp features. It exists in any models because of quantum fluctuations. But quantum fluctuations do not break the scale invariance. So where should we look for the signals? It turns out that we should look into non-Gauss entities. To illustrate that, let's explain what's the scale dependence. So this is a 2-point correlation function. This is a 3-point correlation function. So scale invariance is just the overall scaling of the k. So because the quantum fluctuation does not break the scale invariance, and for power spectrum, this scale dependence is only variable. We know there's no quantum clock signal in power spectrum. That's what we explained. But for non-Gauss entities, independent of scale dependence, there's another dependence in terms of triangle, which is shape dependence. So indeed, the clock signal will manifest as some oscillatory signals in the shape dependence of the clock signal. It looks like that. So now this is the y-axis is the amplitude of a non-Gauss entity, and the x-axis is a scale ratio, is a shape, k1 divided by k3, not just 1k. And for 4 different scenarios, and we see if you plot in this way, we see a very similar pattern as we saw in classical primordial standard clock. And this signal, just because the generality of quantum mechanics does exist in nature. The only thing is the amplitude is very model dependent. So the situation is very similar to a tensor mode. It exists, but the amplitude is very model dependent. Okay, in the last slides, let me try to emphasize advertising the following point of view. So there are many CMB polarization experiments going on nowadays in next 10 years, 20 years, and we will later hear talk from Joe this afternoon. And for the purpose of early universe cosmology, a primary science goal, there are many interesting science goals, but a primary science goal for early universe cosmology is to observationally distinguish inflation from possible alternatives. That's why we are all very excited about the possibility of a B-mode polarization, a gravitational wave in the CMB. That's a well-known opportunity. Here, what I'm trying to talk about is independent of what happened in the B mode polarization, when all these experiments are done, the T mode and the E mode will be measured into a precision which is cosmic variance limited. It's guaranteed. So there's another opportunity in which, in this precision data, there may be some fine oscillatory signals coming up. One of which is the topic of this talk, is a standard clock, can be used to achieve the same science goal as the B mode. Thank you very much. Yeah.
In either the microwave background or large-scale structured surveys, you need the frequency of the clock to be roughly the Hubble frequency, like going back 60 epochs, right? So today it would be large enough scales in the observable universe. You need some tuning to get the frequency to match what we can observe. Right?
Yeah. So there's a window of a frequency which is optimal to observe in a CMB or large-scale structures. It will depend on CMB or large-scale structures. This is right. The frequency typically has to be in the primordial phase, has to be much larger than h. Yeah. But the pattern of the ticks is independent of the mass. So it doesn't matter as long as one of the frequencies show up, you can know what kind of background evolution you have. Yeah. Actually, I have some backup slides here. Just one example using the fitting. We have ansatz, analytic ansatz. And the significance here is not high, is not very high. So don't take it seriously, but just you use this as an example of how the data analysis should proceed. So we have a template where frequency is a free parameter, and we use to fit the residue data of the CMB. And one of them is a full model of a classical standard clock. It's not ruled out, definitely. But it can be tested by precision data in the future, for example, the E mode polarizations. Because this signal has a correlated signal between T and E. And for the E mode polarizations, the error bar would be like that. So it can be tested. Yeah.
What levels of non-Gaussianity become diagnostic for these models?
Yeah. So the non-Gaussianity is a very interesting issue. It's different from different if you talk about classical model or the quantum model. For the classical model, you have to work out the power spectrum first, and the non-Gaussianity is strictly correlated with that signal. So what we have seen so far in terms of experimental constraint, for example, non-Gaussianity is smaller than FNL of order 10, etc., is for scale invariant non-Gaussianities. Local mode, equilateral modes. So those non-Gaussianities are not scale invariant. The classical case, not scale invariant. So the constraint that we have so far publicly from Planck data does not apply for those signals. You need to require dedicated analysis with new templates. In fact, if you look at Planck paper, there are some anomalous oscillatory signals there, and people are still studying that. And for the quantum signal, the study just began. We just published it a month ago. So it's more subtle because there's no breaking of scale invariance, but it's also oscillatory signals, but in shape of non-Gaussianities. So we need to come up with new template, and people have to do new dedicated analysis for that. Yeah.
What value of R actually distinguishes between slow and fast models?
What kind of R? So for tensor mode, as long as it's observable, it has to be fast evolving models. Slowly evolving, diminishing R, like R to the minus 100, something like that. So yeah, even for inflation, it can be as small as 10 to the minus 40 something. Yeah. So as long as it's observable, the slowly evolving model is gone.
Speaking about R, we will hear more later. Thank you very much.
Okay, thank you. That's the speaker.
Oh, yeah.
Hello, I'm excited to talk to you today about primordial planet formation at redshift z of 0.4, and how the planet formation process can link super-Earth's compositional properties to their orbital properties and establish two populations of super-Earths. So a super-Earth is a planet between the size of Earth and Neptune that the Kepler mission discovered in abundance. And lately there has been some emerging evidence that this population is actually two populations of super-Earths. The first piece of evidence comes from the color of these symbols, which indicates the number of transiting planets in the system. Here's a histogram of the number of transiting planets, or tranets as people have started to call them, per system. And recent studies have showed that to account for both the high multiplicity tranets and this big population of single tranets, you need two populations. One population that has many super-Earths in each system that are flat, orbiting in the same plane like in the solar system, and another type of population that has fewer super-Earths or mutually inclined orbits. There's also been emerging evidence that for two populations in terms of composition that are linked to these orbits. So for a subset of Kepler planets, you can measure the planet density by determining the mass of the planet. So these are planet densities versus radius, and there's a huge range of super-Earth densities ranging from rocky planets like the Earth to those that need a low-mass gas envelope. And the mass measurements come from two different techniques. And Lauren Weiss noticed that these yellow symbols, which are planets measured through transit timing variations, the gravitational perturbations between planets in the system, has systematically lower densities than the other planet mass measurements. And this could partly be a selection effect, but it was very intriguing to me because this is one of the first hints we've seen of a link between planetary orbits and compositions. Because to get these transit timing variations, you need the planets to be packed close together. So there's evidence that these closely packed planetary systems also have low density compositions, and that these small number of mutually inclined planetary systems have more rocky compositions. And so now I'm going to present how a framework for forming these planets in situ can naturally account for these two different populations. So here's a cartoon view of how these super-Earths form close to their star. You start out with a disk of gas and dust where planetary embryos are forming, and initially the gas is damping their orbits, preventing them from crossing, so they're stunted at Moon or Mars masses. Over time, the gas is going away over a few million years, and once the gas density gets low enough, these embryos can merge, build a core, and accrete a little bit of gas that's still left over. So this can naturally produce two modes of super-Earth formation that I'm now calling feast and famine. So the first opportunity to feast is during stage one, when you have a disk that has a lot more solids than typical. If you form in a disk with more solids, then you have a head start because you start out with larger embryos. You can undergo just a few mergers to be big enough to accrete a gaseous atmosphere. And you end up with planets with a little bit of gas and tight spacings that can lead to these transit timing variations. In contrast, in the disk with lower solid surface density, you have to undergo many generations of mergers, each of which takes longer and longer because of the exponential dependence of the merger timescale on the spacing. And ultimately, to grow a super-Earth from one of these low solid surface density disks, you take so long that you don't have time to accrete gas, and you're drawing from a huge feeding zone, so you end up with super-Earths that are much further apart. So this is the cartoon view, and now here's the view from our simulations where we're growing these super-Earths and having them accrete atmospheres. And you can see this thicker histogram, which is the planets that end up with gas envelopes, have systematically tighter spacings in terms of hill radii than the rocky planets. So this is a theoretical prediction for a link between planets' compositions and their orbits. There's another way you can feast, though, which is during this stage when the gas is going away. Depending on exactly how much gas there is then and how long it sticks around, some planets can have a lot more gas available to accrete than others. And the gas is also at the same time damping the random velocities of the planets. So when you form in a disk that has a lot of this residual gas in a feast system, you end up with planets with gas envelopes that are more tightly spaced and have lower eccentricities and inclinations, dynamically colder systems. And if you form in a famine disk where there's not very much of this residual gas, you end up with much wider spacings, larger eccentricities, and larger inclinations. So this framework of feast and famine can also account for some other orbital properties of the Kepler sample that have been hard to account for. So these are distributions of Kepler transiting planet properties. We talked about the spacing and Hill radii and the Tranit multiplicity. We can also look at the period ratio between adjacent planets and at the duration ratio normalized to the orbital period, which tells you how flat the system is. If there's a skewed peak here, it means very flat systems. And neither feast or famine alone can produce these distributions. The feast distributions in black make tightly spaced, tight period ratio. They have a lot of multiple tranits, and they have this peak that indicates very flat systems, whereas the famine systems are a lot more widely spaced. That's the red dash one. They have a lot of these single tranits, and this width indicates big eccentricities and big mutual inclinations, so not a flat system. But when we put these two systems together, we get something that matches the observations pretty well. So this is further evidence that nature naturally produces these two types of planetary systems. So I'm excited about these two modes of super-Earth systems because they can link planet orbit to compositions in a way that I don't think we've seen except in our own Kuiper belt before, and naturally produce this type of system that has planets with gas envelopes on flat circular orbits. They're tightly spaced, so they exhibit transit timing variations like Lauren saw the different density, and they form in disks that have higher solid surface densities and more residual gas. The other type of super-Earth system is the famine systems. They end up as rocky planets. They have big mutual inclinations and eccentricities, wider spacing, and these are the ones that formed in a lower solid surface density disk with less residual gas. So I'm excited to try to test this more with the observations, and I'll conclude here. Thank you. I might expect them in the famine type of systems because these ones have this heavy atmosphere that would heat up the planet and make it less habitable. Yeah, so one distinction, especially for like planets in the solar system, when we talk about the atmosphere, we think about the Earth. Here when I'm talking about gas atmospheres, I'm talking about something that's 1% of the planet's mass. So it's something that's really heating up and puffing up the planet and making it look more like a Neptune than an Earth. So it actually, even though Earth has a tenuous atmosphere, I would count it in this category. And it probably outgassed the atmosphere rather than accreting it from the nebula or had it delivered by comets. I wouldn't say that it's between because we don't have a super Earth with a puffy atmosphere. So yes, I would say the solar system formed in famine conditions.
So Bekki, in order to explain the observations, it would sound like these two modes. And does that match what we know about disks from studies around young stars and the development of these high-density disks?
So we don't have great observational handles on the disk properties or what's necessary, though that would be interesting to look at. What we need to know is the solid surface density in the disk, we don't usually have a great constraint on the gas to solid ratio. And when I'm talking about residual gas, this is in models of disk dispersal, you often have a slow stage where the density is gradually dropping, and then you have a fast stage where the disk is draining onto the star. And so this residual gas would be what's the gas surface density just before that stage begins. And again, I would say we don't have a strong enough constraint on the disk mass, particularly in the inner part of the disk where these super Earths are forming, to be able to test that. But ultimately, that would be the goal, to go from the observations of the disk to see how does that lead to this wide variety of planetary systems. Yeah, so one way to, pardon me, interpret this is that this is, in terms of the disk dispersal model where you have that slow and fast stage, this is the gas density before the fast stage begins. And so there's two things that are affecting that. One is the XUV and FUV and X-ray luminosity of the star. That determines at what density the fast stage commences in this type of model. And then also, again, we care about the gas to solid ratio. And we do, at least in as much as host star metallicity is telling us about the proxy, we do have a range of that. So I think nature is making, as far as we can tell, enough span of these initial conditions to lead to these two types of systems.
So are these mutually inclined systems, are they long-term stable?
So they will undergo some more evolution over time, like especially early on, what you care about is interactions on orbital timescales or synodic timescales when you pass each other. And over long timescales, secular effects can start to be important. So there will be more sculpting of these systems over gigayears and tens of gigayears. But in our simulations, we've covered most of the orders of magnitude that they have to survive through. So you may, the thing is that the other systems are more tightly spaced, so I don't even know for sure that one system or the other will persist more over time. But we do ultimately want to integrate these systems for much longer to see what happens. But I think just through the 100 million years that we've covered, we've gotten a fairly good sense for what the final architecture will look like.
I had a similar question, but the mutual inclination is from the synodic interactions in the first place, I assume?
That's right, yeah. And big is relative here. Like these are like 5 degrees. Like it's not the type of mutual inclinations that we sometimes invoke for giant planet systems further out in the disk where they're better at stirring each other with cosi and other effects like that.
Thank you very much.
You have to turn it on again.
I think it is on.
Okay, so I'm going to tell you today about results that are kind of hot off the press or hot approaching the press even. So new results on B-mode polarization from our experiments BICEP 2 and Keck array. This is a picture of BICEP 2 at the South Pole. You can see the sun setting there. So I'm sure everybody here has heard it ad nauseum, right? So we're looking for the signature of gravitational waves coming from the very beginning, from inflation, propagating down through the universe, we're looking for the signature that they may potentially write into the polarization pattern of the microwave background at 400,000 years where the CMB decouples. So we're essentially a remote sensing gravitational wave experiment. So here's a picture of our collaboration at one of our recent meetings. So it's essentially a collaboration of Harvard, Stanford, Caltech, and University of Minnesota. John Kovac here is a very important leader of this effort. And we have some other institutions which contribute, principally key pieces of hardware or instrumentation. So BICEP 2 and Keck array are both located at the South Pole, about 1 kilometer from the Earth's rotational axis. BICEP 2 was the precursor experiment, 2008 through 2011, and basically we multiplied it by 5 to form Keck array. So Keck array is essentially 5 copies of BICEP 2. These are small, compact telescopes using superconducting antennas. We've been focusing on about a 1% patch of sky, so about 400 square degrees, drilling super deep, super sensitive into that 1% patch of sky. So the previous analysis that we did in conjunction with Planck, that came out in February of this year. And that's going to be referred to throughout this talk as BKP, BICEP, Keck, Planck. Today I'm going to report on a new paper that's just about to hit the archive, which adds in the data from 2014 taken by Keck array, and that we're going to refer to as BK14, so BICEP Keck 2014, up to 2014. Okay, so the detectors that we use are these superconducting phased array antennas, and they are scalable, right? So we've been doing all of the observations so far up to now at 150 gigahertz. So that was up until the 2013 season. But we can scale these antennas up and down and go to 95 gigahertz and 220 gigahertz. And so in 2014, we operated 2 of the 5 receivers of Keck array at 95, the other 3 remaining at 150. In 2015, we operated 2 at 95, 2 at 220, and just one remaining at 150. So we've been diversifying the frequency coverage over the last couple of years. So this is the 2014, up to 2014, 150 gigahertz map. So you've got the temperature, the Q and the U components of the polarization signal on the left there. On the right, we're showing the noise. So when we form the maps, we can also form them with a sign flipping procedure that suppresses the signal but leaves the noise intact. So you can see very high signal-to-noise observations of the CMB polarization at 150 gigahertz. This is now 50 nanokelvin degrees, the deepest maps ever made. But what's new for today and exciting are the 95 gigahertz maps from the 2014 data. So this is a much smaller amount of data, right? Instead of like 13 receiver years, this is only 2 receiver years. And so the noise level is higher. You can see that on the right side there. But look at the Q and the U maps as we flip backwards and forwards between the two. You can see the signal is very much the same. This is the lambda CDM E mode, the E mode dominated pattern of the sky. And the reason that it gets kind of more smooth looking at 95 is not because the 150 is noisier, because it isn't, right? It gets smoother looking because the instrument beam, the beam of the telescope, is a little larger at 95 gigahertz. So that is very much expected. Okay, so those are the fundamental maps. So we're going to take these maps and we're going to turn them into power spectra. And these are the power spectra internal to us. So 95 cross 95 as the red crosses. 95 cross 150 as the gold stars, and 150 cross 150 as the green circles. So the green, this 150-150 spectrum we know and love, very high signal-to-noise detection above lensing, so this black line is the lensing expectation. What's new here are the red and the gold, particularly the gold, the cross spectrum between the two. You take the geometric mean of the noise level in the two, and so you've got reasonably good sensitivity in the gold. And you can see that the gold looks like the lensing expectation. So this green here is the dust from our previous analysis, the dust increment over the lensing B mode. And the gold here is the extrapolation of that model down into this cross spectrum 95-150. So you can see the gold looks pretty much consistent with the lensing, the expected increment over lensing from dust. Okay, so we don't just have those 2 bands. We also have 7 bands from Planck now provided over the full sky. Plus, we're adding in this analysis 2 more bands, 2 of the lowest frequency bands from WMAP. So we're doing an analysis, and this is an amusing plot to show on the screen, right? 66 spectra, because we can take the auto and the cross spectra between all 11 of these bands. Now, some of those carry much more information than others, right? Some of them are very noisy compared to others. But we're just showing here all 66. And I don't want you to look at them individually. It's impossible on such a plot. But I just want to emphasize that all of these are going into the likelihood machine. Just to pull out a selected sample of these, you can see at the upper left there, that's low frequency cross hour bands, right? So this is looking for evidence of synchrotron. Perhaps you can see a little hint of it in the 23150, but the 3150 is all low, actually, and doesn't want synchrotron. So it's mixed messages as to whether we're starting to see synchrotron in the data. We, of course, see very strong detection of the dust in the 150-353. That was the main result from the BKP paper. We can also look at cross-correlations external to us, like 23 cross 353, looking for evidence of dust-synchrotron correlation, which is certainly there at the largest angular scales and maybe there at the angular scales that we're interested in here. So we can examine all of these spectra and cross-spectra individually, but having done that, what we actually do is we feed them into a full multi-component, multispectral likelihood analysis. So this analysis, this current analysis has 8 parameters. We've got the 3 parameters for the amplitudes of R. AD is the amplitude of dust, and async, the amplitude of synchrotron. So those are the 3 kind of primary parameters. We also have additional parameters describing the spectral, the frequency spectral behavior of the dust and synchrotron, beta D and beta S, and alpha D and alpha S that describe the spatial spectral characteristics of the dust and the synchrotron, and finally epsilon, the parameter describing the dust-sync correlation. So kudos to local guys Colin Bischoff and Victor Boozer in the audience here. In conjunction with John Kovac, they were the guys who really drove the development of this multispectral, multi-component likelihood machine that we're feeding the data into. So you can see at the upper left there, the thing that everybody cares about, the one-dimensional likelihood on R. Right? So let's examine that in more detail. So the previous result is red here, the BKP baseline analysis from February of this year. And the heavy black curve is the new analysis that we're about to release. So you can see that the peak position on that likelihood curve has shifted down a little, but the curve is also narrowed due to the inclusion of more data. So the bottom line is that, so there's one intermediate step I'd like to call out here. Going from the red to the blue is simply adding the more 150 gigahertz data, and then going from the blue to the black is adding the 95 gigahertz data as well. And both of those shift the peak down a little, but very importantly, adding the 95 narrows the whole curve, improving the constraint. So the constraint goes from R less than 0.12 at 95% confidence to R less than 0.09. Translating into kind of sigma R, the sigma of this curve effectively, it's going down from 0.034 to 0.024. So a significant improvement in sensitivity. Just to compare, those are the one-dimensional curves on R. You can also take that B mode information and you can co-analyze it with the information on R and NS that's coming from the Planck full sky analysis. So that analysis from Planck is shown in the red contours here. And this was the situation. This is basically taken from from the Planck parameter paper. This is the situation that they showed us earlier this year, adding in the BKP data, right? So the contour in this two-dimensional space was narrowing from the red to the blue. Now, there's some model dependence on the full sky derived contours here, and Joe will tell us about that in the next presentation. So you can see that things tighten significantly, going from the previous analysis to the new analysis. So that is what we have for our current efforts. So R going from, including the Planck full sky, going from R less than 0.09 down to 0.07. Okay, so am I really out of time, or was that assuming that everybody else kept the time? Okay, so just to try and summarize this multi-frequency situation that we're now in. So here's the frequency of observation on the x-axis and the noise in the L/80 band power, the one that's critical to constraining gravitational waves on the y-axis. And you can see here 150. 150 is still by far the deepest. The new data are 95, 95. Significantly noisier, but way better than what we had before from Planck at 95. And this is the cross spectrum between the two, the geometric mean. So, and then these are the cross spectra that we take between us and Planck and WMAP. So we're really drilling down way below the noise levels of Planck and WMAP in this 1% patch of sky. So just a teaser for the future, we are now taking data at 220, as I mentioned, and this is just a kind of pretty picture showing that we're mapping the lambda CDM E modes at high signal to noise at all three frequencies. So this is actually just the 2015 data, and you can see very high correlation between these three E mod sky patterns. And how will that translate into the noise level in the power spectrum? So this is just adding one extra point for the 220, 220. It's already in the power spectrum about 10 times more sensitive than the Planck 220. And we'll limit dust about equally well as the Planck 350. And that's only going to improve. So just to conclude, the BICEP Keck program is currently leading the field in terms of this quest for gravitational wave signal. We have the best published sensitivity to date and the best control, proven control of systematics at the degree angular scale range that we're operating at. We're today adding data from 2014, for the first time including 95, and we're pushing down the 95% limit on R from 0.12 to 0.09. Now, okay, that might sound incremental, right? But I'd like to emphasize that it's kind of an important milestone. So for nearly 20 years, people have been talking about setting limits on gravitational waves or potentially detecting them using B mods. And for the first time, we're doing better with the B mods than you can do with the Planck TT constraints. And those are limited now. Those are fully saturated against cosmic variance. They're not going to get any better, even if you had a more sensitive spacecraft. So it's really... B mods are really starting to fulfill their long-held promise, and we can go much further. In 2015, we're adding in this 220 data, and we can anticipate a reduction in sigma R still further. BICEP 3 is now online at the South Pole and should come up to full power this coming season. That's an all 95 gigahertz super receiver that will massively accelerate the pace at 95 gigahertz. And we have very big plans for the BICEP 3G array, as it's currently being called. This would be essentially an array of BICEP 3s. So we had BICEP 2, we had an array of them called Keck array. We have BICEP 3, we have an array of them called BICEP 3 array, right? Very imaginative. So this can potentially take sigma R down to 0.005 or perhaps even better. So thank you very much. Uh-huh. So lensing is no fundamental barrier, right? It's just a foreground. It happens to be an achromatic foreground, right? A foreground that has the same frequency spectrum as the CMB. But fortunately, it's a non-Gaussian foreground. So there's actually information within its own structure that tells you about what it is. So potentially we can de-lens. And we're starting to work very hard on that, actually. As soon as we get this paper out, it's kind of the next thing in the pipeline analysis-wise. We need to start trying to de-lens for real. So theorists have done it 10 years ago in papers and shown that it's in principle possible. Now we need to prove that it's in practice possible. And we're confident that we can. The question is, how much can you de-lens? Factor 2, factor 5, factor 10, what can we do? And that's going to be a big challenge for the next coming years.
You said you have the best signal support now. You didn't say by what factor.
Okay, so the question is, how much better are we than the competition? And the answer is at the moment a lot, because there are very few other published results from B mods. So, Well, I believe Joe is still correct that there's no B-mode result from Planck on R. Or maybe there is. It's under-publicized, right? But it's considerably larger.
Yeah, it wouldn't expect to be.
It's like factor 10 larger in sigma R, I think. There are many other experiments that say they're going to get there, right? That any time now they're going to have results on sigma R, but there are none published at the moment. I mean, there are older experiments that had much larger numbers, but the current generation is still coming. And the second question was, how long to 0.005? Well, it depends whether we get the money for bicep 3 array, but bits of it, right? I mean, we're looking 3-4 years out, something like that. Yeah. I mean, look, we can build these things, and we know of no reason why we can't do that. So.
As usual, I'm the wrong clothes for one of these microphones, never mind. Okay, so I'm actually not going to quite talk about what Clem was advertising. I was going to talk about. I want to talk about a problem. Well, I want to raise something that, if we don't pay attention to it, could become a problem in cosmology, which is our ability to measure the optical depth to reionization. Okay, it's interesting from reionization perspective, but it's actually really important if we're going to measure things like neutrino mass, if we want to measure curvature better, if we want to get dark energy constraints. Getting the optical depth better than it is now is, we need to do it. And we're not quite there yet. So just a reminder, the optical depth tau, it shows up in the CMB primarily, is there a pointer? No, I'll just wave my hand. Primarily in the, so we've been hearing from Clem about the power spectra, the larger scales in the CMB, E-mode and B-mode power spectra. Here's a multipole scale. And the E-mode power spectra is shown here with this bump at very large scales, peaking at L of about 4 or so, where you're getting that reionization signal because the universe is reionizing, redshift 10, redshift 7, etc. And you're scattering the intrinsic CMB quadrupole off these ionized electrons. And that scatter produces a polarization signal, and you get that bump. And the size of this bump scales with, if you increase the optical depth, you increase that bump. It's not super sensitive to the reionization history. For example, up here, I'm just showing an example of 2 different reionization histories as a function of redshift, the ionization, either going up sharply, too high a redshift now seems unreasonable, or more gradually. And the impact on the E-mode power spectrum is different, but it's not massively different. Essentially, you're really sensitive to the optical depth. But right now, thanks. The current status of the measurements from the CMB is it's okay. We haven't seen significant improvements in the last years that we had hoped yet from Planck, although I believe that new Planck analyses are coming soon. So this is just a sort of summary of the probability, the likelihood of different optical depth values as a function of the optical depth here. And the sort of canonical one right now is the Planck measurements combined with a combination of doubly map and LFI Planck low-frequency measurements of polarization, cleaned up with the Planck 353 maps that Clem was just talking about too. And that's there, here. Optical depth about 0.07 or so. But the width is it's not as tiny as we hoped it would be by this time. If Planck had been without any systematic issues at all, which it has been a bit at large scales. And And one thing that certainly came out was that our estimate of the optical depth from WMAP went down by about a sigma when we used the better Planck dust measurements. And that gives you a sense, and that was kind of it was a bit more than I think we'd expected, but was of the order we'd expected in terms of our foreground uncertainty in the optical depth. I would say that the current estimates are still perhaps a slightly under-characterized the uncertainty due to foregrounds in our current estimates. It's really hard measuring the larger scales looking through the galaxy. And we now have better measurements from Planck, but those scales are harder to deal with than the ones that Clem just showed at degree scales. Anyway, so why is tau correlated? Why does it matter? If you increase the optical depth, you make reionization happen earlier. The CMB temperature anisotropy is suppressed more. It scatters more, and you get an overall reduction in amplitude of the temperature anisotropy of the CMB, the higher the optical depth is. And so you get this long correlation, this degeneracy between the primordial amplitude of fluctuations and the optical depth. Is degenerate along this direction. And this sort of ellipse here shown already is truncated by having polarization measurements. From temperature data alone, it's much longer. So we measure with the CMB an overall anisotropy, and that is this combination of tau and primordial amplitude. So we don't know what the primordial amplitude is because we don't know what tau is. And so if we then go measure the amplitude of the matter fluctuations at later times, then they're a function of the primordial amplitude and everything else that can then affect the growth of structure. So that's neutrino mass, curvature, dark energy. And without having that kind of initial anchor, it can be a little problematic. So just this is an illustration of that forecast that my student Rupert Allison did just recently, which shows the forecast predicted constraints on the optical depth against the neutrino mass. And similar results come out for curvature and dark energy too, where here we're looking at the combination of measuring the amplitude of clustering via CMB lensing and distance ratios with baryon acoustic oscillations from DESI. And the only difference between these three plots is how well you've measured the optical depth to reionization. Okay, so the outer one, the blue one, says I've got current measurements from the WMAP reionization optical depth. Okay, it's pretty broad. The inner one says that Planck worked perfectly, and I have the correct optical depth measurements that Planck managed to do. And the inner one says I've basically got a cosmic variance limit measurement of the optical depth that I can achieve from CMB measurements, from its effect on the CMB. And for example, here for neutrino mass, it's super important because this is the minimal mass we expect of neutrinos. If we can achieve this inner contour, then we get a 4 sigma detection. If we're stuck with the blue one, we don't get a detection of neutrino mass. So it's really important. And it's, as I said, it's a very similar, propagates through to measurements of curvature and dark energy. And it's important not just for measurements of CMB lensing, but also for other measurements of growth. So the matter power spectrum is seen through other probes too. And it shows in a slightly different way. It's an argument for why with CMB observations we should be motivated to try and get down to as large scales as possible, because this just shows in a different way. For example, in this case, this is neutrino mass, but again, this is just one example where as I go down lower and larger scales in a CMB experiment, the uncertainty. Let's say I've only got current measurements of optical depth from CMB, then if a new CMB experiment could push only to L scales of L of 20 or so, then I'm stuck up here. But if I can come down to the largest scales, I can shoot down to interesting levels. So the issue is that getting to those large scales is really hard. So solutions. one path is we just have to be aware that we really need to make these better E-mode measurements. And it's not just, there's obviously the fascinating reionization physics is a good motivation too, but this impacts the other cosmological measurements. So we can try and make better measurements. It's interesting that because the scales at which the reionization peak starts are around L of 15, 20 or so, if you could even just get to there coming down, you're actually sort of doing pretty well. And we'll see if measurements from the ground can manage to do that. There's also the Lightbird satellite that's being proposed that might get down there, that if it flies, could make that a beautiful measurement. And I think that's a good motivation. I'm also really curious, and I'm actually eager to see what people here, what their opinion is of it, is that you can obviously use non-CMB measurements to try and measure the optical depth, and that can help. So, for example, here's a forecast done recently by Adrian Lewitt and others showing that if you can add 21 centimeter observations where you basically shrink tau down to this kind of narrow region, then again, you break the degeneracy quite strongly and you improve your measurement on, for example, neutrino mass quite a lot. But I'm not yet, I don't know enough about these, the kind of confidence that we'll have in these measurements for precision cosmology. As I'm actually curious to know what people here think about that as a path forward. That's it.
Interesting point is that if you're just interested in tau, all you need is the global signal. You just need to know when hydrogen disappears.
Yeah.
How did it disappear as a function of redshift? And for that, you can integrate across the sky and just get the temperature of the CMB as a function of frequency.
Yeah, and so that seems more doable and less model dependent, right?
Right. That's less information than usually the 21 centimeter experiments are aiming at. They're aiming at mapping the
power spectrum. Yeah.
Rather than the global.
But do you think that one's coming up in the next, in 10 years, do you think we'll have this?
Well, that's the forecast here, that ERA, that will be the next big instrument. If it's funded again, then they might get it. Because that usually is more complicated, as we found with the BMO.
Sure, yeah. Well, they'll also have to deal with foregrounds too, right?
Exactly.
Yeah.
Questions for Joe? Everything was clear? Oh, Clem.
So, Joe, sorry I misbilled you, but
It's
there
fine.
is an impact, presumably, from tau on the R constraints.
Yeah.
Because that's where it's coming from, right? Low LCT, up or down, is R or no R, and tau is also pushing that around, right?
Tau pushes the whole of TT around. So it shouldn't affect so much the constraints on R from TT because the TT just cares about the relative balance
so
of...
no degeneracy even if we introduce running as well, model extension?
Maybe if you introduce running, but I think that... I think because we should think of roughly that tau is just broadband, everything up and down, it looks pretty different to the kind of the other primary parameters that would affect the temperature. So I don't think it's strongly correlated with those ones.
Got our family. Thank you very much.
Actually be in Oxford in a couple of weeks.
Oh, cool. Yeah. Are you giving a talk?
So this is actually kind of people. So you are pretty much done with your visit, huh?
Yeah, getting back to Bombay.
Okay, have fun.
Okay, thanks for.
You're smart. You're leaving just as it gets more.
Oh, yeah.
So 95 by 50 is the intensity of the noise. Because the 150 is not way lower noise. 95 by 50 is much better than 95, 95. And then, but all of the differences. Oh yeah, no, there's a whole context of those. So we do all of the usual tests till 95.
So they have to give the candidate, and then sometimes legal projects can even
Several manual methods. Many So now we have to grab sequences down, right?
Oh, good. Okay. I know already.
I worked with Jill for summer at Oxford, yeah.
Yeah.
I went to the Oxford course.
yeah.
No, but because I was there a lot, I
Yeah, David Spurl just was like, what is it?
Go to Oxford.
Yeah, go to Oxford.
yeah. Because you're working with, you said you're working with Abby and with Daniel. Yeah, cool. Yeah, okay. I guess I didn't really ask you what you were, in more detail what you were doing.
Oh, I'm sorry, I had to run to
Oh, good. Really?
Yeah, exactly.
It's a bit like this. Did you go? We get the back. Yes. Oh yeah. Yeah, exactly. Yeah, no, you should definitely take it. I'll just grab it.
So good to see you.
I didn't even know that you were not. You were. Anyway, I lost track.
Yeah.
That's great. So yeah, so you're applying to see it. Okay. So yeah, you're doing it.
Yeah, so I'm doing it on the road 16. All right, did you know or does it?
Yeah, you too. Yeah, it's.
I used to work in Cambridge University.
Oh, yeah, okay.
I went there once. It's a very popular town, Cambridge.
Oh, it's terrible. Yeah, terrible.
It's very close, but somehow they make it as much as possible.
They don't want to see each other.
Yeah, exactly.
Yeah. But I'm interested in this idea of maybe testing these.
Yeah, this
Right?
Yeah, precision data for emos.
Yeah, the emotes, yeah. And I'm so excited. Emotes, anyway, like this. Once you've measured them properly, there's way more information. Yeah.
Could be some structures coming up.
Yeah, absolutely. Yeah.
Thank you so much. So looking forward to your...
Oh, cool, thanks. Cool, let's see you then.
Exciting.
No, it's good, it's good.
You met the students before?
Yeah, I did, yeah.
this place was trashed. He's in the meeting. That's good. That looks like a good spot. Over here, I said, Bob, in romper room in here, huh? I was like, I know 3-year-olds that can keep a place cleaner than this. And their marks that are going around picking stuff up off the floor and shit. It's like, really? It shouldn't involve a mark either. No, it shouldn't. Bob, let's bang on Phillips. You know, earlier when I was sitting in the office, him and I were talking and stuff, and I was like, hey, Sus, don't feel like, you know, we're not out to get you if you feel like uncomfortable or anything. If we ask you to do something, we shouldn't have to come to you to tell them to have them do it. I mean, what, we have to stop what we're doing to call you to stop what you're doing, just to stop and go there and tell them? It makes no sense, buddy. We're not out to get you in trouble, you know? I was like, you don't know what's going on unless someone says something. By that time, it's usually too late. Because the shit's hitting the fan. It's afraid to do something. Anyway, it's an excuse, dude. Nothing for nothing, but it feels nice in here. Nice and cool. I know they're going to be crying later about that.